If you want to do a hydration reaction without the possibility of your molecule rearranging, you can do an oxymercuration demercuration. In this reaction, you will form a mercuric cation. The OH will add to the more substituted position, and we also form a bond to mercury acetate. Another second step will remove the mercury to leave you with just the OH and the H here. In solution, the mercuric acetate will lose an acetate as a leaving group, which will form the mercuric cation, which can then be attacked by the nucleophile. So when the pi bond attacks the mercuric cation, a carboxyl cation forms on the more substituted carbon, and the alkene or the pi bond is attacking this, and it goes to this side because this is less sterically hindered. This is the mercurinium ion. Mercury still has a lone pair that can attack here. That wants to join in on the fun. So the positive charge moves to the mercury. This is the mercurinium ion. We have the positive charge here, then there is this positive charge here. When a nucleophile comes into proximity of this mercurinium ion, the bond between the mercury and the carbon will weaken, giving us two partially positive sites. The nucleophile then is free to come in and attack here. The mercuric acetate goes onto this carbon that is less substituted. The nucleophile adds here. It may seem strange that the nucleophile is attacking this more substituted, somewhat sterically hindered carbon, but the nucleophile is better on this carbon than the mercury, which is a large group adding to this carbon here. So mercury goes to the carbon where it has more room to hang around, and then we have this bond that forms here. So this is our electrophile. This reaction can be used with water or an alcohol. We first add the mercuric acetate with water. That will form the mercury on this carbon, and the water will go to the carbon that is more substituted. That would still have the mercury on there. The second reagent we need to add is sodium borohydride. This replaces the mercury with a hydrogen. If you add the alcohol, the O is still the one attacking, but we have our R group, so if this was methanol, it would be the methyl group here, and the H gets picked up via a proton transfer, and then we have the hydrogen here. So we can form the alcohol or the ether. These are both Markovnikov products. The OH or the OR are adding to the more substituted carbon, which is the Markovnikov product. If you want to reverse the regiochemistry and achieve the AntiMarkovnikov product, where the alcohol is adding to the less substituted position, we use a different reagent. This is boron, BH3THF, with hydrogen peroxide and water. 90% yield for this one. This is the Markovnikov. With BH3 and this reaction, we can get enantiomers. So there's one where the methyl group gets pushed forward, one gets pushed back. One thing that you'll notice, however, is that the H and the OH add to the same side. You would not get addition of the H and the OH on opposite sides. So this is an anti addition and also a syn addition. In the hydroboration mechanism, electrons will attack the boron, or this is treated as a Lewis acid. So these form these partial bonds, and then this hydrogen here, the electrons from this boron-hydrogen bond can start to form there. So the electrons from the hydrogen-boron bond go to there, and then we've got this bond to boron forming. Then there's the BH2. That group will get pushed back. B adds to less substituted. The B would rather have its own space bubble than to get added to the more substituted carbon. That is the hydroboration part of the reaction. It's usually followed by an oxidation step. The peroxide that is added, the OH of that replaces the Br. So this electron lone pair from the oxygen goes to the B. Those electrons inserts an oxygen. We add water. And you do not need to know this mechanism, but it's there if you wanted it. In this reaction then, boron will get added to the less substituted carbon, and after you add H2O2 OH-, the OH replaces the boron. If one chirality center is formed, you will get a racemic mixture. We would get an OH here. In this reaction, when we add the OH, we're actually forming two chirality centers. It would still be a mixture of enantiomers. Here are two practice problems. This is Markovnikov. We will add OH to the more substituted carbon, and this is water, so that's why we're adding OH. This is the AntiMarkovnikov. OH will add on the opposite side of the methyl group, but syn to the hydrogen. I would get this product plus an enantiomer. You can draw the product plus the enantiomer or write the product plus the word enantiomer. This type of reaction is a little bit different in that this falls under the reduction category of reactions. The ones that we've been doing up to this point have been the functional group transformations. This one is reducing because we're adding hydrogen across a double bond. This is called hydrogenation. We go from the alkene to adding two hydrogens across the double bond. This happens in 100% yield. This reaction, as you can see, involves using hydrogen gas, which sounds like fun, but I always found it to be terrifying because I knew a fire could break out at any point in time. This is also a syn addition. The metals that you can use are palladium, and those are the catalysts. You can use platinum and also nickel. If you do form a chirality center, again, that is going to be a syn addition with a chiral center. The H is going to add to the same sign of the alkene pi system. So the way this works, we have the metal and the hydrogen gas will sit and coordinate onto the metal. The alkene can then come down on top of that, and the hydrogens will add from the same side, so we end up with the cis addition or syn addition. The products here, this will end up with H's on either side. You can draw the hydrogens in or leave them off. This would be a reduction reaction because we are gaining hydrogens. In this reaction, the same thing will happen. One product will be more likely than the other. When you have a group that is facing this side, the bottom side is going to be favored for attack because we don't have the steric effects of that. That would push this forward and the H's go back. In a halogenation reaction, we're going to add 2 halogens across a double bond. If you start with petroleum, we can get ethene, then we can add chlorine. That happens in 97% yield. We can then do an elimination. This is vinyl chloride, which is the precursor for polyvinyl chloride, or PVC. You may have seen that in piping. We can do this halogenation reaction with chlorine, bromine. Those are really the 2 ones that can be used. I2 is too slow. F2 is too violent. For the stereochemistry of this one, we've been seeing reactions where things add syn to each other. In the halogenation, the products will add anti to each other. And because they're doing that via their mechanism that they go through, we can get enantiomers as well. The alkene usually serves as the nucleophile. This is the halogenation, an electrostatic map, and you can see that it's polarizing itself. So even though Br and Br are the same electronically, they can polarize themselves to make a partially positive and a partially negative end. The nucleophile can attack here, form the bond plus Br minus. If we were doing the reaction with cyclopentene, we would see a nucleophilic attack. This is the nucleophile, this is the electrophile, and also loss of leaving group. When this attacks here and those electrons come back down, we form what is known as a bromonium ion plus Br minus, and that is positively charged, making this partial positive and this partial positive. This bromine is now the nucleophile, and it can attack either of these electrophiles, and it will do so from the opposite side of the bromine. They don't want their electron clouds interfering with each other, so this is going to come in from this side. Those electrons come up. So nucleophile hug, loss of leaving group. And this is down here. These are anti to each other. This reaction with cis-butene will give us the anti-addition. we get enantiomers there. If we do this reaction where there might be some steric interference, the bromine next to the wedge here will be preferred on the bottom side, so we still have the anti-addition. This would be the major. Once you form a bromonium ion, if there's water present in the reaction, the water can act as the nucleophile, and it can do a nucleophilic attack or hug, and then we have the loss of leaving group. So you get this plus the enantiomer, and the water present can do a proton transfer. To get the alcohol. This is a halohydrin. If it's chlorine, plus the enantiomer. The halohydrin reaction will give an anti-product. For regioselectivity of that reaction, the Br will go to the less substituted and the OH goes to the most substituted. And the reason for that is after this nucleophilic attack, we know that bromonium ion is formed. When water, the nucleophile, attacks, it will go to this side because this bond is weakening. This is in a similar fashion with the mercuric acetate reaction, where the Br would rather be by itself, just like the mercury. So this bond weakens, and that's why the OH attacks there. Then we do a proton transfer for the OH. Bromine is big, would rather be by itself over here. Water is small and it can fit in there to attack.